Okay, we'll start with this one. And as I said just already, that this is the last lecture or set of lectures last week of the first part of the module. So once we finish this week, we're halfway through. Next week, we switch over to a lot more design. Okay, and we start to look at software design patterns, and we look at how those patterns can inform our designs then. Okay, if you look at the current assignment, you'll see, let me just go to that assignment. I think I have it here. Okay, if you look at the current assignment, it's a 3-week one, and it's not so bad, you know. The whole point of this particular one and giving it this length of time is that you might say, well, there's a lot of stuff in here that we've done already, okay? And this is going to be dead easy. I leave it until the last couple of minutes and do it, you know, the last day, okay, and get it done. We're going to be much, much more observant of your design in this particular assignment. I want you ultimately to be able to reflect on the work that you have done already and say to yourself, was this program just written? Was this program designed? Can I do a better job on this? Can I go back and look and reflect on how my code works, how it was put together, you know? And you'll notice that in this particular assignment, there is an undo redo requirement. So I want you to be able to start adding shapes and different kinds of shapes and so forth to your canvas in terms of SVG, and then I want you to be able to remove these shapes and so forth. But the reason I'm getting you to do this is because later on in the module, in a few weeks' time, we'll be looking at formal methods or formal approaches in order to do this undo and redo. We'll be looking at 2 design patterns in particular, one called the memento design pattern and one called the command design pattern. Okay, and so I want you to think about ways you might do this. I'll tell you now, start thinking about having a stack or something and then pushing something onto the stack, and then, you know, you save the current state of the SVG canvas, push it onto the stack, push it onto the stack. Every time you issue a command, push it onto the stack, yeah? And then you undo is simple to remove it, yeah? And redraw. So that's how you ultimately do this. But the other thing I want you to think about for this particular assignment, especially for students who haven't actually got to the point where they're trying to get some extra marks to do the extra credit part, this is a great opportunity for you to try to get some extra credit. Okay, it's a great opportunity because a lot of the work that you've done can be redone and reworked. You know, the interfaces, the command line stuff. I put up just before the break, I put up a small application which was a menued interface. I don't know if you saw that, by generating that. Like, that didn't have a graphical user interface, and you don't have to have one for this. But that's a nice menu-driven system that shows you how you can pull all these things together. You can use this if you wish, okay? Or you can use the one that's in the assignment that's required. You know, it doesn't matter what way you want to do this, okay? We want to have some feedback to the user, okay? So reuse whatever you have already, try to improve on it, and try to get to a point where you think about doing that extra credit. Please, you know, every single one of you are capable of doing this, okay? So try do it. Get those extra 5%, yeah? It's really, really important for you to start thinking about it. Even give it a go. It should be in your mind, I'm going to go for the extra credit this time, okay? And it's important, and those of you who have attempted the extra credit will know that the most important aspect of this is that you think about doing the extra credit at the beginning of the assignment, okay? And you will have got that from CS230 as well, okay? Because you don't want to be making too many changes to your program, okay? Sometimes what's important about this is that the design of the program will differ if you start trying to factor in the extra requirements. Yeah, and that's really, really crucial here, is that it's not just about coding and then adding in another bit. You actually have to change your design sometimes in order to make it work. And that's where a lot of people might finish their assignment early and then decide, I'm going to do the extra credit now, and then realize, oh gosh, I can't do that. I have to undo too much in order to be able to do this. Yeah, you've come across this feeling? Yeah? Okay, so the way to not do that, have that feeling or that experience, is to start thinking right from the outset, I'm going to do this, all of this. Okay? That's the way to start thinking about it. And even if you don't get to it, you'll still have a fairly decent design that will work for you. Okay? So this is the way to go about this assignment. Okay? Assignment 3, there's only 2 left after this. I can tell you one is about implementing the memento pattern. One is ultimately about implementing the the command patterns. Okay, lots of, so this, you know, you could at the end of this have 30%. Okay, maybe even if you've done the extra credit in the other ones and have got those marks, you could actually have passed the module at this stage. Okay, 40% already. Yeah, you could be done in terms of passing, but that's not good enough. You want to be getting the 100%. Okay, so this is important for you. I know I labored it, put a little bit of time in here, but I want you to do well, guys. Okay, I really want you to do well, and this is the time to start believing in yourself and start doing this. Yeah, and ask for help. If you think from the outset, I can do this, I want to do this extra work, I want to get this extra credit, that will help you ask the questions in tutorials. Use the labs productively. You have 3 weeks, you know, loads of time to do this. It builds on what you've done already. Any questions before I move on? No? Okay, we'll move. Okay, so we're going to look at designing. Ultimately, this week we want to look at designing class hierarchies using UML. Have you come across UML before? Show of hands, yeah. UML, how many? Okay, some haven't, some haven't. Okay, so the people who've done the UML, was that as part of CS264 in software engineering, or was it, what was it? CS264, yeah, okay. And some of you have not done this, okay? So you're gonna have to up your game and do this. I tried to put everything in this one slide, but it's very dense, okay? A bit like UML itself. And I mean dense in terms of it's hard to read, it's terse, not the other dense. Okay, so we're going to see how ultimately UML can be used to describe software design patterns. So in order for us to get into the next section and understand design patterns, we have to be familiar with being able to read UML diagrams. So I'm going to show you some today, point out some of the nuanced stuff. And in the short lectures, I'm going to show you how you can use, the short lessons, I'm going to show you how you can use Plant UML to design your own UML. Have you used software tools for designing UML in the past? What did you use? Star UK, yeah. I don't like it. Okay, so I won't repeat it on the on the voice. But yeah, I never use that one. Okay, but I'm notoriously lazy, you know, and in terms of so I tend not to use this one. But I use Visual Paradigm, which is my go-to piece of software. I like it. It's free for you guys to download and use for 30 days, and then you can delete it and do it again, perhaps maybe on a different machine, whatever, you know, do whatever you need to do. You won't need to use much. So the 30-day license is pretty good for this course here, okay? So you'll be fine with that. But I tend to use an extension called Plant UML for VS Code, because I use extensions for everything, and I'd recommend you do this. What's important to note as well is that you will be expected to submit your designs. Okay, so when you have something designed, you will be expected to submit your UML diagrams for your code. So we want you to have an object-oriented solution. So we need proper classes, we need then some inheritance hierarchy, we need to know all that stuff works. Maybe you might have to build abstract classes. All that stuff that comes from a design would be really important. And we want to see these designs submitted with your assignment. Now you can automatically generate these. Okay, you can generate these with Plant UML as an extension embedded into VS Code. And I'll have a short lesson, first of the short lessons that will appear tomorrow, will show you how to do this. Okay, so it's not like it's anything too arduous. Okay, so we're going to have a quick review. Lots of words on this. You know, I'll give you all the notes. You don't need to start writing things down, but the unified modeling language is key to all of our descriptions of designs and patterns. Okay, and modeling then, what is modeling? Okay, it's designing of software applications before coding, okay. Thank you. It's an absolutely essential component of large software projects. Now we're talking about large software projects with many tens of designers involved and maybe millions, tens of millions of lines of code, ultimately. Okay? It's helpful to medium and small projects, and there are different kinds of models. There's a formal model, and there's a which is a mathematical sense, and there's a visual model, which is the UML. Okay? And the model plays this analogous role in software development that designs and plans play in the construction of buildings or vehicles. You guys are software engineering, and this is a software engineering course. You don't just go out and build a house without plans. You can, but you know, you probably wouldn't get approval for what's been done. Okay, Same thing with designs. You're going to have to start moving from writing code to designing code and designing applications. The code will follow, okay? So using this software model or design, engineers responsible for software development project success, they can be assured that the functionality is complete and correct, the end user needs are met, and the program design supports requirements for scalability, robustness, security, extensibility, and all the other characteristics before the implementation. In code renders changes difficult and expensive to make, okay? What's essential here is, and I had a really interesting mail. I get this mail every year, and I get it every week, actually, every year, where, especially when the assignments are done. Students tell me they worked hard on their assignment. I have no doubt they worked hard on the assignment. They put a lot of effort in, they wrote a lot of code, and they didn't get the marks that they expected. Why? Because you're not meeting the requirements. It's the core. First of all, the program has to work. Okay? You don't go out and buy a car and find that it doesn't work. Looks good, has nice wheels, you know, lovely alloys, all the stuff, brilliant engine, but actually doesn't work. No use. You don't go buy a house and find that one of the back walls is missing, right? You're freezing at night. Every cat in the country is coming in and sleeping in your bed, right? You know, that's not going to cut it. You don't get marks for things that don't work for the requirements. That's the simple line here. You need, the reason we publish in this module the actual marking scheme is because that tells you and shows you the importance of the requirements. I don't care how much work you spent. If you don't meet the requirements, you don't get the marks. That's reality of software development, guys. You are senior developers now. You're third year students. You have to start realizing that delivering is absolutely crucial. That's where you get the marks. It doesn't matter at this stage. We don't really matter how well it's delivered, okay? How well it's been designed, or if it's not been designed up until now, you know. We will in the next few weeks, a few assignments. But what's important is that, you know, you understand design right now. The service shows that large software projects have a huge probability of failure, okay? In fact, it's more likely that a large application will fail to meet all of its requirements on time and on budget than it will succeed. It's a brilliant book if you can ever get the book. It's called Why Software Projects Fail. Have a look at that. And modeling then is the key development success tool. That's why we have this stuff. That's why we talk about design. Okay? I want you to get that into your head. If you went away with anything from this lecture, this slide is the most important slide. The rest is just how to do it. But knowing how to do something is meaningless unless you understand why you're doing it. Okay? Crucial. You need to understand that design is really important. So UML then allows us to be able to raise the level of abstraction. And models help the design by working at this high level of abstraction. It can do this by hiding or masking details, bringing out the big picture, focusing on different aspects of a prototype. My perspective on doing apps is that, like, for example, I often say to you to don't care too much about the user interface. And when you were doing CS230 for me, you got no marks for how well something looked. As long as it worked, that's all that mattered. It was the functional stuff that mattered. Because it only started to matter when you start doing like software CS280, where we look at interface design. So I tend to look at everything from the UI and the interface. And then, unless I'm doing the back-end stuff, then I'm really interested in the REST API descriptions. So it's all about the model. So the OMG's unified modeling language helps you specify, visualize, document models of software systems, okay? And the OMG stands for Object Management Group, not the other abbreviation. And it's an international open membership, not-for-profit technology and standards consortium. You see this everywhere. I don't really care about that stuff, just it works, okay? And it works well. But using the UML-based tools, you can analyze an application's requirements, design a solution that meets them, represent the results using UML's 13 diagram types. How many diagram types did you come across and use when you were doing your software engineering? These people put their hands up. Will I ask a question from somebody who's actually here? I know I won't. Anybody want to tell me what types did you use? Class diagrams, yeah? Everybody does class diagrams. Did you do databases? Did you do entity relationship modeling? That's a kind of UML diagram as well, okay? And it helps you visualize this stuff. Did you use interaction sequence diagrams? No? Yes? No? No, no, no. Okay. Okay, so if you think about the class diagram, what does that tell us? It tells us about the static structure of the code in a way. It tells us of the components of that code. How do we describe how the actual code runs and how the various components interact with each other? How do these classes interact and behave? How does the message passing work between one and the other? That's an interaction sequence diagram. Where does the interaction sequence diagram come from then? It comes from, any ideas? No? No? Maybe look that up. Okay. Everything comes from our original specification of the use cases. Use case diagrams. Did you do those? Yeah, okay, so use case diagrams tell you what happens and what components are there. Use case diagrams tell you a little bit about how the system responds to human input or any input, yeah? Then from that, we're able to design the classes. Once we have the classes and we get the objects from those classes, we can have a deployment diagram. We understand how the interaction sequence happens. Okay? All that stuff can be formally documented and then makes its way into code. That's why we have the design. They're not diagrams that are independent of this, okay, of what's actually happening. I'll give you a tip now. Now, when you get to fourth year, you'll have a major project to do. Most of you will be involved in a major software project, okay? And we expect students to have design. So students often, I spend a lot of time correcting students, and I'm sure there's many a student that would be really unhappy to find out that I'm correcting their thesis, but you know, because one of the questions that I ask them is like, I love your design. Lovely UML in your thesis, looks brilliant. Now tell me, how did you actually get a piece of code from this design? And more often than not, they can't tell me. Because it just was something that looked good. And I think, oh, I have to have it, it's here. So they lose marks because they didn't actually use the design to build the software. Okay? I have a nasty trick that I play on students sometimes when I'm teaching software engineering, is that I split the class into groups, and each group starts building, they've got a piece of software to develop, and they start with a design. So they build a design for their software. And then what we do, we swap the designs around between all the groups. So they don't actually build the software from the design that they built. They build it from somebody else's design. See, what happens is that they know what software they want to write. So they write it independently of the design that they've created because they think it's just a requirement. And then it becomes really difficult because they actually have to design from the design or build from the design. Students get very upset at this point, you know, and it's not intended to make them upset. It's intended to be a learning experience where you actually see the importance of design. It's like having house plans and say, oh great, I've got these house plans. I'm going to build a house I want. I can say this is the plan. This is what's happening. This is the most important part of software design module. You need to understand there's this connection between your design and the code that you result. So what can you model with the UML? Okay, it defines 13 types of diagrams. Okay, 13 kinds of diagrams that you need. That you rarely will use all of these. Okay, but there are 3 categories: 6 diagram types for the static application structure, 3 represent the general behavioral structure, and 4 represent the aspects of interaction. So we have structure diagrams like class diagrams, object diagrams, components, composite structures, packages, deployment. Behavior includes the use case diagram, activity diagrams and state machines, and interaction diagrams are derived from behavior diagram, which are the sequence diagram, communication diagram, timings, interactions, overview diagram. As I said, for small projects, you will never come across many of these, or any of these. Okay? So here is how they all relate to each other. So in fact, it's really interesting because it's using the UML to describe the UML. The language, a visual language is used to describe itself here in many ways. And you'll notice that I've highlighted a couple of them. We have the class diagram here, and we have an interaction diagram here, sometimes called an interaction sequence diagram in a way, because it gives you the sequence of events that happens. And it's nice because once you have the class, the static structure from the classes that you can generate the objects, then you can look at the interaction sequence that happens between those. So it's interesting to know that these things work together. Okay. So the structure diagram shows the static structure of the system and its parts and the different abstractions and implementation levels and how they're related to each other. The behavior diagrams show the dynamic behavior of the objects in the system. And that's a series of which it describes how the system changes over time. Okay? And this is very interesting for you because you have this static structure in your program, which will be your SVG canvas, which is represented by some kind of object. And you have the behavior where you receive some input from the user, and that behavior then changes the state of the internal state of the system, which can then be rendered and drawn. Okay? So I want you to be able to look at the assignment in the terms of the design. How do you design the interaction? How do you design it? What does the interaction do? How does it impact on the state of the system? And how does it ultimately impact on your overall coding of your design? Yeah. So we're really only interested in then later software design patterns with C#. We're going to look at class diagrams, object diagrams, and sometimes sequence diagrams for behavior, okay, behavioral structure. So here's a class diagram. You've seen some of these before. You can see these. Is it too bright? Can you see this diagram? Sometimes the blue doesn't work too well. So it's a central modeling technique that runs through all object-oriented methods. And this diagram describes the types of objects in the system and the various kinds of static relationships which exist between them. And there are three kinds of relationships. We have associations, we have simple associations or straightforward associations, which we just refer to as associations. And then we have dependencies as well. So we see those dependencies. We have inheritance, and we have aggregation and composition. Now, you'll have seen all of these before, okay? A lot of time when we talk about building classes, we try to figure out, well, how or why do we put the classes in this particular way? Why do we design the classes this particular way? Okay? Sometimes it just feels right, okay? But that often isn't enough, okay? It needs to go beyond feeling like it's the right one, or looks good, or seems right, to being a good design that you can actually say something sensible about, okay? And you mean this is a complex, in many ways, class diagram here, compared to the very first design pattern that you'll see, which will be the singleton pattern, and the one class, okay? And these then are very simple design, the simple model here compared to an actual working model in a large organization application. So there's a lot happening in this. Okay, so you can look at this and say, oh yeah, that's it. Or you can actually read the diagram. Okay. So what I need you to do is to read the diagram. Okay. I've got some red marks here. There are some red indicators here which give you some good information about what's actually happening. Okay. This particular piece diagram was taken from my go-to reference for revising my modeling information about the UML. I don't go to the original books and texts at this point. Once you've read them once, you don't want to go there again. Okay, in many respects, there's a lot of material to digest. I tend to use the Visual Paradigm website because it has a really good help section and it's a digest of all the material that we need. Okay, so it's worthwhile going there and download the app while you can, if you wish as well. It's a nice app. I have it here, and I'll be showing a demo of using it a little bit later. So it's nice. It's a Java-based app, and it'll run on all of your operating systems. So I need you to read this. You know, we have a customer and order, corporate customer, personal customer, order line, product. We've all of these classes. We've got to ask ourselves, why do we have them? Where did it come from? What are they representing? What are they fulfilling the requirements here? What's this generalization here? What's the difference between generalization, association, and operation, and so forth? Well, we know this is a class, and we know we've seen before that classes have attributes and methods here. Okay. So this is our static structure. Our generalization, we know at this stage that this essentially refers to inheritance, the inheritance hierarchy here. Okay. And we see that corporate customer extends customer, personal customer also extends customer. So these are new classes as well. We have customers have orders, or in some way are related to orders, or are they? So one customer, we have cardinality, what's here. One customer can have many orders. That's a star. It's hard to see, but it's a star. And then we can say an order has one or zero or more order lines, and each order line has a a quantity number of a particular product, and the product here, so there'll be 0 or more of these. So we need to be able to read the diagram. Okay, read the diagram. Don't just look at the diagrams, read the diagrams. When you read the diagrams, we get from this, it tells us everything we need to know about creating the static part of code that represents this. You know, in fact, I could replicate this in 2 minutes using visual paradigm, and I click a button and it will generate the C code for me, C# code. It'll generate the Java code for me. Whatever code I want to generate, it'll do C++ code. Okay, I don't actually have to write the code anymore if I don't need to, because we've designed it. And the beauty, of course, is that if I change the design, I just press a button and it rewrites the code for me. Okay, easy. Yeah. And we can go the other way. We can have code, and then sometimes because we write code, we can generate the actual class diagrams from the code as well, which is what you're going to do in a way, you know, as well. Okay. Because what I want you ultimately to do is I want you to implement a design pattern later on. And when you implement the design pattern, then I want you to actually generate the code generate the UML from the code that you've written, and then compare it against the design pattern. So it's like it's a sanity check or an integrity check for you, so that you can say, well, I started out with this model, and you like say we get to the memento pattern, or we get to the command pattern, or I might need you to implement a singleton or something like this, and I say, well, okay, I started doing this using informed by this design, and I'll give you the book that I use a little bit later. I'll give you the details of that book. And now that I've written the code, I want to actually check and see, am I actually meeting the design? Okay, so I start with the design, build my software. I want to then compare my software to see design and comment on it. Reflect on the design. Was the design actually, did it meet with my original, or did I deviate? If I deviated from the design, why did I deviate from the design? Yeah. Oh, look, I had this plan for a house, but I decided to build an internal wall. Do you know? Yeah. Bought this lovely car, but decided, like, you know, I was going to add some spoilers because it makes it look good, you know, or whatever. Yeah. Doesn't matter. The point is that it is what it is, but you need to understand and see how it fits with the design. Yeah. Okay. And I want you to start thinking about that kind of stuff. These need to be read, okay? They don't need to be looked at. They need to be read. All right. Yeah. Start learning, kind of read it. And look, it takes practice, guys. Okay. It really, you know, it takes, and you may get it wrong, okay? But just look at it and try to write out a few sentences and say, what's going on here, you know? And then go back and see and check and see, does that make sense? Yeah. Start doing this, you become a better designer. I know from interviews, for example, where students say that they're into design, they use the UML, they go, and the interviewer will go, oh great, you know, and they pick out a UML diagram that they have a print to hand ready, surprise, surprise, and say, tell me what's going on here by looking at the design. You should be able to know what's happening by looking at the design. And this is the exact same thing. I studied physics way back, almost like seems like a lifetime ago. But I remember at one point being at a design meeting for some. I was doing atmospheric physics, and I was building some software and hardware, which was a controller for an observing station. I was looking at what was happening in the likes of the aurora borealis, you know, in the sky. You know, I was interested. So I built this stuff. I was trying to design some circuits, electrical circuits and electronic circuits, and then build the hardware that could interface with a computer. Well, I went to talk to a man who's a electronic engineer, and he says, "Oh well, I'll show you what we need to do." And he pulls out this big sheet of paper and he unfurls it, and it was a circuit diagram, electrical circuit diagram. And he says, "So read that part there. That's the part you need to replicate in yours." You know, and it's just like resistors, transistors, capacitors, op amps, all that stuff, right? All the stuff. But you had to read it and make sense. So I had to say, yeah. I mean, it was hard going, you know. But that's the kind of thing that happens in those kind of interviews. You're given to say, well, what does this do? Yeah. I wasn't too bad because I was always interested in building radios as a kid. So I was able to read circuit diagrams. So I learned about how to build my own radios and communication stuff. So I had a bit about reading these circuit diagrams. But it's hard at the beginning, you know, really hard at the beginning, but you'll get there. And some people get the fourth year and they can't even read code, okay? So, I mean, that's really shocking stuff. But please, at the very least, be able to read a design, okay? Okay, so some things that we looked at then, if you look at some of these things here, we see there's an association here and there's a generalization here. There's also a couple of more important bits in terms of the UML design, one called the aggregation and composition. And I have my obligatory cat, which I added afterwards, but it's important. And you can click the link here to the visual paradigm discussion of the differences between association, aggregation, and composition. And you know, if you want your own copy of a cat, you can click on the cat and download it there as well. It's a free image. Okay, so this is a really good example. Okay, so we have an owner. I have pets. I hate the notion of being the owner. You know, I kind of like. Anyway, they're just somebody who live with me. But then I have cats, so that's cats for you. So we have an owner has a pet, which may be a cat or a dog, for example, or a ferret or whatever, you know, a pygmy goat, I don't know. But this particular pet is a dog, and the dog, for example, has a tail. Thankfully, you know, given the new docking laws, most dogs have tails these days. But there's a cat wandering around as well here, okay? And you may or may not own the cat. The cat may own you, who knows, right? But anyway, we see that there's these relationships here. We have that the owners feed the pets, and the pets please the owners, and you know, we map all sorts of human traits onto these animals and believe that, you know, they're human. So, but either way, it's an association. We have pets, or we care for pets. We have this association aspect. And the same thing happens with various objects. One object having another object in there, okay, relates to it in some form of association. Then we have a tail, and the tail is part of both dogs and cats, so this is aggregation or composition here. The tail doesn't exist without the pet, okay? If the pet's destroyed, the tail is destroyed. Doesn't work the other way around. Sometimes they dock the tail, the pet still exists. Barbaric, but yeah, you know, it happens, unfortunately. But in terms of a design, we know this is aggregation and composition. A cat is a kind of pet. I say kind of pet because, you know, my cats live with me because they want it, but they could leave if they wanted tomorrow, and I'd understand it, right? But this is a kind of inheritance from pet, okay? Whatever your notion a pet will be, okay? So we have this notion of generalization and inheritance. So we have this aggregation composition. There's also another kind of aggregation and composition here. So they're very close to each other. And sometimes people make this mistake and don't understand what's going on. So if two classes in a model need to communicate with each other, so we need to think in terms of communication, in terms of relationships. It's all about communication, okay? It's not about owning or having and all this kind of stuff. It's about communication. There has to be a link between them that can be represented by an association, which is connector. It's a solid line across here. Okay? Sometimes we see a dashed line. I'll come back to that, okay? Then we have this aggregation where we have this open diamond here. And they... So let me just say, for the association, we sometimes have a line with the class and an arrow, which gives you the navigation direction, okay? If an arrow is on both sides, the association is known as a bidirectional association. Okay? We have an aggregation and a composition and generalization. I'll do these in the next slide, but we can indicate the multiplicity of the association by adding multiplicity annotations to the line denoting the association. So there's lots of examples in the document here, and you'll see, sometimes you'll see the star, 0 star, 0 dot dot star, 1, in, all that kind of stuff, right? Not in, star. Okay. So what's the difference then between association, aggregation, and composition? So aggregation and composition are subsets of association. That means they're specific cases of association, and in both cases, one class owns another class. Okay. So aggregation implies a relationship where the child can exist independently of the parent. So a class, okay, this class, and the student, okay, the parent could be the parent class for a class, and the child class are the students. If you delete the class, in other words, we abandon CS264, I know you'd hate that, but the students will still exist. You should be doing something else, yeah? So in a model, this is how it works. The composition then applies to the relationship where the child cannot exist independently of the parent. Okay? So if you're modeling a human with components, you know, you've head, heart, you know, you remove one, well, the other doesn't exist anymore, okay? One goes, they all go, okay? So it's important to understand that composition implies this relationship where the child cannot exist independently. The parent is a very strong life cycle dependency here. Again, I'll be quickly on this one because we use generalization to describe the methods for combining similar classes of an object into a single or more general class, and that identifies commonalities among a set of entities. They could be attributes, behavior, or both. The superclass or the parent has the most general attributes, operations, and relationships that can be shared with subclasses, and that's basically saying that generalization is all about inheritance, and a subclass can have more specialized attributes and operations. And specializations then is the reverse of all of this. We create new subclasses from an existing class, so that's easy. I did mention I'd come back to this notion of association here, and here we have class A having an association with class B, and we can see that there's a solid line with the arrow. So where the association, again, as I mentioned, is unidirectional, class A knows about the other class and the relationship, but the other class doesn't. Okay? You might believe that you own the cat. Okay? The cat doesn't know that you own the cat. It might be the neighbor's cat. Okay? But you have that relationship because it comes to visit you every day and you feed it. Yeah? Yeah. Such associations require an open arrowhead to point to the class that's known, and only the known class can have a role name in multiplicity. I feed my neighbor's cat. Okay. A dependency then is different. It's a weak relationship between two classes, and it is represented by a dotted line. And it exists between two classes if the changes to the definition of one class may cause changes to the difference of another class, but not the other way around. Okay. A lot of words here today, you know, a lot of language around all of this stuff. And the reason I'm doing this quite deliberately, I'm quite deliberately not talking about code. I'm talking about dogs and cats and humans and cars and houses, okay? Is because the model transcends everything, okay? It's about describing the world. It's about describing the mini world that you're creating in your software. It's about describing the interaction between the human and that program that you're developing. Okay? It's essential that you understand that the models are language. And the models are just really nice, succinct, visual ways of representing the actual language, representing the existence and the interaction and what's happening here. Okay? You have to get this. This is serious stuff. Okay? All of this, all that stuff is succinctly represented by these two boxes and these arrows. They have meaning. They're not just two boxes now. They have meaning in this context, okay? Yeah. And they need to mean something to you as software engineers. They're not going to mean anything to the untrained person on the street who's not involved in software engineering and software design. It doesn't need to. But it needs to mean something to you, please. It's absolutely essential that we have this. Okay, so this is a diagram. That's a UML class diagram that really, it's a bit, you're going to see more, as you see more and more diagrams, they have more and more classes. And really, you have to look at this and say, well, what's happening here? What's going on? Okay. It's not actually that different from assignment 3. Really, it's not that different from assignment 3. We have this window, which could be your canvas, okay? Yeah, for your SVG canvas. Yeah. And it responds to events. The events here, it is dependent on the events. Okay. So the event is, the command that you get. yeah, from the user. Then it sits within some frame, you know, so that doesn't matter too much. It's just the window, the application that sits, that's basically the app. And we have this aggregation here. It contains shapes. The shape is the abstract class, and we have some generalization where we can create circles, rectangles, polygons, and then we have a composite. These are composed of points. Yeah. So it's not too different from the kind of thing I'm asking you to do. Points don't exist independently of the shape. Now that's mathematically we could, and philosophically we could argue this. Well, this is a design. It's not meant to describe something philosophically. It's telling us the way things are as far as this program is concerned. It may not actually be the reality of things, mathematically or philosophically or whatever. It tells us from the description of our program what's happening here. Okay? That's what's going on. It tells us that's the way it is. Yeah. And also tells us that circles, rectangles, and polygons all extend shape. We have something here which is tells us a little bit about engaging with the window. We don't have to worry about that too much for ours. And we have a drawing context, you know, here as well. So how it all happens. So these would be, you know, converting what we have in our describes our shapes into the SVG, for example, yeah, on the canvas and so forth. Not exactly the same. It's a drawing application. You essentially have a drawing application, albeit it's not using a graphical thing, but it's describing the graphical, and your representation of the drawing is textual in a way, you know. But you could imagine, I hope, that this design, you could produce a design that looks a bit like this for your application in assignment 3, or in fact any of the applications that you've done already. Does that make sense? Yeah. This is the kind of thing we want to see now. So when I want you to think about a design. But initially, you know, you can do this and look about a design if you want. And if I was you, I would be like have my pen and paper. You know, they're great. Pens and paper are brilliant. Okay, I would draw out my pen and paper representation of this. It's enough. I would probably photograph the pen and paper, say draft 1. And you know, the great thing about pen and paper, as you probably saw when we did CS280, for prototypes, paper prototypes are great. You know, they cost nothing, very little. And if you don't like it, just rip it up and start again. And it's easy, yeah? There's no real investment of learning a tool and all that kind of stuff, because you all know how to use a pen, I hope, at this stage, right? So, so draw it, what you think it will look like. Then write your code from that. And then generate your SVG, generate your UML code using plant UML to see what the diagram actually looks like and see how it relates to your initial design. Yeah? It's beautiful to be able to do and see this. And there's a real sense of accomplishment, I find, that when you have looked at a design and then you write some code and then you generate that UML and you start seeing the comparison between the two, and it really starts to come together that I designed this program and I wrote this code following the instructions of my design, and yes, it is actually a designed application. There's a real sense of like accomplishment here, and it should be, and you should have that feeling of that I've done a good job with that. Okay, that's what we're trying to instill in you now. That makes sense, yeah? You guys need to be designers, not just coders. I know you can code, okay? Most of you can code. Some of you struggle a little bit, but you know that, and you're doing better, okay? And there's room to get better, and get better, and get better. And part in a way of using a new language here for this particular module to move you away from Java, move away from these things, is that everybody's kind of on the same footing again, you know, with coding, and that you don't spend all your time thinking, oh, I know how to do this in this way, and this way, and this way. I want you to get from the design to the code, you know. That's why we do it a little bit like this. There's a bit of control going on for me here, okay, to try to have this sense of like, well, this is new, you know. There are two main kinds of classes. We'll stop here, and there are a good many more slides, and I will break the remainder of this into two 10-minute sessions in the short lessons, okay? But let me finish this slide, and when we'll finish for today, if you don't mind, please. The boundary classes, they're used to model interaction between the system's surroundings and its inner workings. And this interaction involves transforming and translating events and noting changes in the system, the interface. Okay? Those are the boundary classes. And the control classes, they're used to model or control the behavior specific to one or more use cases. So control classes encapsulate use case specific behavior, and the behavior of a control object is closely related to the realization of the specific use case. Now we don't have use cases, but actually you do have use cases because I'm telling you how the use case works in the assignment. I'm going to quickly go back to the assignment and just remind you that this is a use case. I'm actually telling you here how the program will run and how it works. I'm telling you how the system responds to user input and how it behaves. This is a use case. A bit like the user stories we would have seen before, but it's a use case. It tells you how it behaves. And you need to be able to replicate how it behaves with your system. So from this, you should be able to determine the static objects, the boundary objects, the control objects, the hierarchy of all of these objects, how they all fit together, the interactions, the sequence, how that works. Build a model, draw it on paper, start coding, and then look at how it will work with your code from UML. And I'll show you how to do that in a short lesson as well for tomorrow. Lots to do here, guys. You've done UML before. This may be a slightly different take on it, but I really want you to take away, I need to design stuff and generate code from my designs. And then generate designs from my code and see how I really understood what was going on. That's the takeaway, okay? And you're all very well capable of that. And just a reminder, start looking at this assignment in terms of, I want to get the extra credit here. Look at the bigger design picture, okay? Every one of you is capable of doing this, so please go for it, okay? Thank you very much. Have a good day.